Hello everyone, this is Muskan Singh and today I am going to explain you the topic metric spaces. So its definition is let X be a non-empty set, a mapping D of X cross X into R, where R is the set of all real numbers, is said to be metric on X if and only if D satisfy the four axioms, and they are: the first is dxy is greater than or equals to 0, where x comma y belongs to X. M2 is dxy is equals to 0 if and only if X is equals to Y. Uh, M3 is dxy is equals to dyx, where X and Y belongs to X. And M4 is dxy is less than or equals to dxz plus dzy, and here xyz belongs to X. M4 is also known as triangle inequality. So if D is a metric space for X, then the ordered pair X comma D is called metric space, and dxy is called distance between X and Y. Thus a metric space is a non-empty set X equipped with a metric D on X and is denoted by the pair X comma D or simply by X. Different matrices can be defined on a single non-empty set, and this gives rise to distinct metric spaces. Now, what is pseudometric? A mapping D of X cross X into R is called a pseudometric for X if and only if D satisfy the axioms M1, M3 and M4 of above equation of metric on X and the axiom M2 dash. Here M2 dash is different, which is dx comma x is equals to 0, where x belongs to capital X. Note that for a pseudo matrix dxy is equals to 0, even if x is not equal to y, dxy will be equals to 0. Thus for a pseudo metric x is equals to y, dxy is equals to 0. But conversely, it follows that every metric is a pseudo metric, but a pseudo metric is not necessarily a metric. Now, distance of a point from a given set. So its definition is let xd be a metric space and let A be any non-empty subset of X. The distance between a point P belongs to X and A is denoted by dp comma A. Here P is the point and A is the subset. A is any non-empty subset. So dpa distance is defined as infimum of dp comma x, where x belongs to A. Uh, Here it is evident that dp comma A is greater than or equals to 0. Also it is evident that dp comma A is equals to 0 means distance between P comma A can be 0 or greater than or equals to 0 if P belongs to A. Now, what is diameter of a subset of a metric space? So its definition is let xd be a metric space and let A be any non-empty subset of X. Then the diameter of A, denoted by del A, is given by del A is equals to supremum of dx comma y, where x comma y belongs to A. The diameter of A is the supremum of the set of all distances between the points of A. So the diameter is a distance of all the set of all the distances between the points of A. So here between all the distances we will take the supremum value and it will known as the diameter. If dA is less than infinity, then the diameter of A is said to be finite, otherwise infinite. And if dA is less than and if dA is greater than infinity, then A is said to be bounded. So let's take an example on metric spaces and try to understand how to solve these questions. So the example given is let xd be any metric space. Show that the function d1 defined by d1 x comma y dxy upon 1 plus dxy. Here dxy is already a metric space. And value of d1 xy is given, where xy belongs to capital X is a metric on X. We have to prove that d1 x comma y is also a metric space. So to prove this, we have to prove the four axioms. If it satisfies all the four axioms, then it will be known as a metric space. So firstly, it is given that D is metric on X, defined as D1 x comma y dxy upon 1 plus dxy whenever x comma y belongs to X. Then D1 is metric on X as shown as. Now firstly, we prove the first axiom, which is M1. Now we have dxy is greater than or equals to 0, as dxy is a metric space as given in question, where x comma y belongs to capital X. Now since we know that dxy upon 1 plus dxy will also be equals to and greater than 0, as dxy is greater than or equals to 0 for xy belongs to X. So, and we know that it is equals to d1 xy. So on substituting its value, we will get d1 x comma y is greater than and equals to 0 for xy belongs to X. So our first axiom is proved here. Now let's get on the second. So the second axiom is M2. We have d1 x comma y is equals to 0. It means if we put d1 x comma y is equals to 0, it means that dxy upon 1 plus dxy will also be equals to 0. So, and we know that dxy is equals to 0 if and only if x is equals to y, as d is a metric on X. So dxy is equals to 0. Now, so by this we have proved it that d1 x comma y is equals to 0. Now let's come on the third axiom, which is M3. We have d1 x comma y is equals to dxy upon 1 plus dxy. So here d1 x comma y can be written as dy comma x upon 1 plus dy comma x, as dxy is equals to dyx. So we have written dyx in place of dxy. So we know that according to the definition given in the question, it will be equals to d1yx. So here d1xy is equals to d1yx. So our third axiom is proved. Now let's come on fourth axiom. So let x, y, z belongs to capital X. These are the three terms which are in capital X. Then we can write it as d1 x comma y is equals to dxy upon 1 plus dxy is equals to 1 minus 1 upon 1 plus dx comma y. We can written it as, on separating the numerator and denominator, we can write it as, now d1 x comma y will be less than and equals to 1 minus 1 upon 1 plus dxz plus dzy, as if we add something in denominator, the overall value will always